Hello, my name is Matt, and I'm going to talk about the ATTiny85. So I've been using the ATTiny85 for about 8 years, I'd say. And recently I had to do a very simple project where it was the right fit. And while I was doing that, I thought I could make a little tutorial video that talks about the chip, its pros and cons, and gives a little demo of how to write a simple blinking light program for it and load it onto the chip. So that's what this video is all about. So to start, let's take a look at the chip. So you can see it's a 8-pin DIP in this version, and it looks a lot like a 555 timer. You can also get it in an SMD version, so that's how the size compares for those. And I'd say it's about a third the size or so. And which I'll bring this up later as well, but there's a close sibling to the ATTiny85, which is the 84. So the 85 has 8 pins and the 84 has 14 pins. So with this you get 7 extra data pins, which can be helpful for some projects. So moving on real quick, I just wanted to show some projects that I've done in the past. So this one, you just put it in an RC car and it will blink the light red if the battery's low and blink the light green if it's okay. And as you can see, there's just a couple of parts and it was all thrown together probably in less than an hour from thinking of the idea to having something. And then here's another similar kind of hacked together thing where I just wanted to do special flashing lights in a pumpkin. So that's that one. And then a slightly more advanced project. So this is a charger for A123 rechargeable batteries that I made. So you just plug that in and then you can plug this into a charger here. And the ATTiny85 part is just a voltage meter. So if you hold the battery here and put this here, it will tell you how much charge is in the battery. So let's talk about the pros and cons of the chip. So one pro is it's a great fit, as I've shown, for simple projects. One of the big reasons is because it has a lot of built-in features that allow you to eliminate parts. For example, you don't need to have an external oscillator, so that saves you an oscillator and 2 capacitors. The other nice thing is it has a wide voltage range, so it can take 1.8 to 5.5 volts, which often means for many projects you can connect a battery directly to it and don't need a separate voltage regulator, again saving parts. The other thing that's nice is it can drive up to 40 milliamp per pin. So if you need to drive a power transistor or drive an LED directly, this thing can do that. So again, saving parts. It has deep sleep modes. So you can run this thing in a sleep mode where it's only taking a few milliamps of power and listening on a pin for a pin to change or its own internal little watchdog timer to go off before it wakes up. So it's pretty straightforward to make projects that run on batteries and last for years with this thing. And then the one more thing is it's a relatively easy chip to master. So if you're on a learning journey with microcontrollers, you could learn this thing top to bottom a lot easier than a more complicated chip. So, and then that can be a foundation for future learning, which I'm a big proponent of. Cons. Okay. Low pin count, obviously. You can talk I2C with this thing pretty well because that only takes 2 pins and you can talk to multiple devices that way. If you want to go SPI, you often have to hack it a bit to make it work. I've definitely done it personally. Or, like I said, just go to the ATTiny84 and buy yourself 7 extra pins if you feel like that is needed. The other issue is it has limited RAM and flash. For the 85 version, there's actually a 45 and a 25 as well that have less. But the 85 has 512 bytes of RAM and 8K of program memory. So by modern standards, that's pretty small. But for the projects that this thing is used in, it's usually enough. The other issue with the limited amount of RAM is like the standard Arduino library which was designed originally for the ATmega 328P, is going to be a bit heavy for this. So you'll probably want to use AVR GCC and program in C directly, because that buys you a lot in terms of code space. And my example will be going through that. And the other thing is the chip itself is not particularly cheap. I think in very low quantities, like a couple of chips, these are $2.50 each, $2.50. And these are like $1.50 or something, which, you know, much more powerful chips will be similar prices. But you have to remember the much more powerful chip might require 3.3 volts. So you might need, depending on what you're talking to, a bunch of support circuitry to get the power. So, and also you might need more board space. So the cost might come closer than you expect at the end of the day. All right, so let's move on. So now I'm going to talk a little bit about how to program these things. So starting with the dip chip, you can buy commercial things, but I just made this myself. So it is a Arduino Nano clone that I've just programmed to be a ATTiny85 programmer. So with that, you just put the pins right on here and you can program it. You can also buy a dedicated ISP like I did here. And I think I got this for $11 for 2 of them, I think. And this just has a little 6-pin header. So in this board case, I just have the 6-pin header right there. And it's just a 1-to-1 mapping to the pins with no extra circuitry needed. And then the last way that I'm starting to experiment with is I have this pogo pin adapter I made. I might make a separate video on that, but it's just the pins line up directly with the ATTiny85, and you just line it up, and then you don't need this extra header. All right, so moving on, we're going to talk about how to write code for this that blinks a light. Let's go. Okay, so now we're going to talk about the tools that you need to develop. Now you can use Arduino, but I wouldn't recommend it because the Arduino libraries tend to be a bit bloated, so you won't get the most out of the ATTiny85 in terms of performance or memory usage. So just look up AVR, GCC, and whatever operating system you're using. Here I'm using Linux, but to be more specific, I'll just say Ubuntu, because every Linux distribution has its own way of doing it. Okay, and then just follow the directions. So in this case, we just run these commands here. Okay, so we could do that. I think I have them all, but it doesn't matter. I'll just do it anyway. Oh, I guess there's something oh, GDB. Okay, and okay, because I've never actually used this specific computer to debug or to upload the code. AVR dude is used to upload the code, and I don't know what that is. Oh, that's a serial library, FTDI. So sure, we'll install them. They're not very big, as you can see. Done. Okay, now if I type AVR GCC, it'll say no input files, which tells me that it's installed. Okay, now we can start looking at code. So to do that, I actually have a GitHub project called ATTiny85 link somewhere. There it is. And this only has 2 files in it, makefile and blink. So we'll take a look. So here's how you blink a light. All we're going to do is turn a pin on and off. So at the beginning, this is all just comments. It tells you that this is how we would hook up the chip in this for this code to do what I asked it to do. So NC means not connected. So most of the chip is not connected, as you'd expect. And then you have power, which can be anything. I think 1.8 to 5 will run the chip, but you need a certain minimum voltage to actually light up the LED. So I said 3 to 5. and ground, and then any pin you want can be the LED. So in this case, I picked LED for PB3. And then of course you need a resistor in there in order to keep the LED from getting burnt out when you turn on the pin. So here's the code. So I said pin 3. So there's this, well here I'm just setting a constant. So I'm just lighting up bit 3. So 1/3 will end up looking like this. So that bit there will be lit up. Whereas if I said or, 1, 0, which you wouldn't have to put the 0 in there. You could just say or 1. Then this would be lit up. And then this pin here would also be lit up. At the same time, they would blink together. So you could do that if you wanted, or you could light them all up, whatever you want. In here, this is data direction. So by default, when you power the chip up, all of these are high impedance inputs, which is a good way to start up. So basically anything that's hooked up to them will look like they're hooked up to nothing. To a degree. I mean, if you put a high voltage over here, then it will flow through here. But if you're using reasonable voltages that are within what the chip can handle, then it's just going to look like it's not going to accept any current, but it will measure it. So if we set this here, it's saying take pin 3 and actually make it an output. So now it will either drive that to VCC, which will be 3 to 5 volts, whatever you give it, or it will sync it to ground. So here we're going to do that, and that's called port. So these are special magic variables that the compiler actually turns into assembly code to manipulate the hardware. So this is the data direction, and this is the port. So or equals means light up this bit of port B. So that's going to turn this to high volt, or to VCC, which will turn the LED on. Then we're going to wait 1 second, 1000 milliseconds. And this little caret thing here says, so LED here is 0, 0, 0, 0, 0, 1, 0, 0, 0. Got extra 0 in there. Whereas in here, it's going to be 1, 1, 1, 1, 0, 1, 1, 1. So that little caret says, take every 0 and make it a 1, and take every 1 and make it a 0. And then this is an AND operation, which says take everything that's there, and if there's a 0, make it a 0. If there's a 1, leave it the way it was. So these OR and ANDs are just a way of changing that one bit, because port B is actually all of the pins. And that's why up here, you could light up multiple ones if you wanted to turn multiple ones on and off here. So hopefully that makes sense. And then we wait. And then we just do that forever and ever. Well, as long as it has power, we do it. All right. So now we want to compile it. So we'll type make. We'll look at the make file in a little bit, but we called AVR GCC with a bunch of options. A lot of these options, you could probably get away with not using them. We'll go through each one. So this says we're using an ATTiny85. You can use this to compile for a number of different chips. This says our CPU frequency is 1 megahertz. -G just means attach symbols to the compiled object, not the final binary, but that lets you disassemble it. OS means optimize for size. This these three says if you happen to have unused functions in your code that are never called, strip them away. This just says what subset of C rules we're going to use, so we're going to use C11. These two are give me as many warnings about the code as you can. It's very helpful for catching bugs before you put it on the chip. And this says make every warning an error. And this W no array bounds, certain versions of the AVR library actually break that warning rule, so we have to turn it off. and then there's the file. AVR object dump, this is an optional thing which converts your output to assembly. So when you ran this, you got a file called a.out. And this is going to convert that into assembly, just so we can look at it. And then this converts your a.out into a hex file, which can be uploaded by AVR Dude onto your actual chip. So let's take a quick look at a.s. A very quick look. So this is your code compiled. So at the top, there's just a bunch of sections telling you where the memory regions are. And then here we're actually starting the code. So we start with an interrupt vector table. Because we didn't set up any interrupts, the only one that's set is the reset vector, which happens when the chip is reset. And what that calls is just this little bit of code here, which actually sets a lot of things the way that they are already set, but it sets like the stack pointer and the status register and a few things like that. So that's just to get the chip in a good state if it's in a weird state but happens to reset itself. Now we're onto the code we actually wrote. So you can see here this constant actually isn't doing anything because it's just for the compiler only. Okay, here we're setting that LED to DDRB. So 1/3 is, like I said, 0000100, which is actually the same thing as an 8 in decimal. So that's being set here. So DDRB, this is being put into a register, and then that's being moved to 0x17, which is the hardware register DDRB. Okay, this is the while one, and this is doing the same thing, except that it is turning on the LED. So SBI means turn on a bit. So this is port B, this 18, and 3 is bit 3 because we told it bit 3 up there. So our delay call actually is running a bunch of code between here and here. This is a jump, which is just designed to take as much time as we asked it to. And then here we use CBI, which turns off the LED. So 18 again for port B, CBI is clear bit, and 3 is 3. And then we have that same little block of code that does the wait again. As you can see, you could put this in a separate function if you wanted to save a few bytes. And then we just go to the beginning and we do it again and again and again. So that's the assembly code. I normally don't look at the assembly code, but I think it's worth looking at the assembly code occasionally, and especially if you've never looked at it, because it can be a little instructive. And the only other thing I'll talk about here, so here is the hex file. So that's the file that the AVR Dude software is going to load onto the ATTiny85. So it's the same thing as that assembly file we just looked at, but it's got all of the comments stripped away, and it's just down to the actual code that the chip needs to run. And then finally, the make file. And this is just rules. So you could type all this stuff out like I did in the make file, but it's easier to just use a make file. So I don't want to go into super detail, but basically it's just, I need this file and this is how I make it. So that's it at the computer. The next step, we will actually load it onto a real ATTiny85. All right, we got our classic blinking light test. So this is the code. This is assuming that it's running at the same megahertz that this is running at, which I don't know. This could be running at either 1 megahertz or 8 megahertz, and this is going to be compiled assuming that it's at a certain megahertz. If it's wrong, then it'll either be blinking way too fast or way too slow. So let's see. Let's go ahead and make the code, and then let's just go ahead and upload the code and see if it works at all. Okay, so I'll plug this in. Make sure everything's on camera here. All right, make upload. Okay, and it looks like the light did turn on, and it's just staying on. Maybe it's in the way too slow mode. It's hard to say right now. Oh yeah, it's in the way too slow mode. 8 seconds instead of 1 second. So it must be set to 1 megahertz, but the code is set to 8 megahertz. So just a quick fix for that. I'll fix it in a second, but we'll just make this 10x faster so that we can see the light blinking. And then I'll fix the frequency in a second here. Okay, so that should blink a little bit faster. There we go. Now we're blinking a little bit faster. Okay, so now I'll show you how you can actually change the frequency of the chip. First thing we have to do is we have to read a fuse, because these fuses say set up a lot of things on the chip, including if it's external or internal oscillator and what speed the internal oscillator should run at. So this is the cryptic command that you use to read the fuse. It's the low fuse. We're reading it and putting it in binary. So it's 110 0010. And that's actually the startup values that you get that they make in the manufacturer when they manufacture the chip. So if we look at this here, we can see what these values mean. So clock output enabled, that outputs it on a pin, that's off. Startup time setting, that's off. Clock divided by 8, that is actually on. That's why we're running at 1 megahertz. And clock source setting, that'll let you run at 8 or 6.2. These little links here will tell you, but you can run at 8 or 6.4, I should say. So what we want to do is take that 0 bit there and flip it to a 1. And I actually have a makefile rule for that, so that I get all the options right. So here we're just going to set it to easy too. So let's go ahead and run that. So I could type this AVRDO command in myself to get the same effect, but I like the makefile because I can review it all before I run it. Okay, so now you can see we're actually running at 8 megahertz instead of 1 megahertz on the chip. And then to fix the code, we just have to tell it that it's running at 8 now instead of 1. And then recompile the code. And that will recompile delay timers and things like that so that it has the new megahertz in mind. So let's go ahead and upload that. Okay, now we're running at 8 megahertz and blinking once a second. So now we're set up to do something a little more interesting with this chip. So I'll set that up and demo that real quick. Here's a slightly more interesting example. So the only thing I have here is the ATTiny85 and an OLED display. And here we can have a voltage meter for a lithium battery. So there's no voltage regulator, there's no resistor divider. There's a lot of the parts that you would normally need for this are not necessary because a lot of it's already built into the ATTiny85. For example, the chip itself can be powered anything between 1.8 and 5.5 volts. So we're taking advantage of that here. And there's a built-in band gap reference that we can use to compare the voltage that we're getting to a known source so that we can figure out the voltage. And as you can see, it powers up nice and quickly and does the job. Now, this isn't the most ideal or accurate way to build one, but the point is you can make very simple projects with very few parts. And a lot of times they'll meet the requirements that you have. So if you're interested in learning more about how to build this, let me know and I'll make a separate video on it. Alright, I hope you enjoyed my little overview of the ATTiny85. And if you have any questions or you think that there's a good point that I failed to make, feel free to leave a comment. Feel free to leave a like if you found the video helpful. And note that I have a number of other videos that you can check out that cover similar subjects. So with that, have a great day.